Hello, I'm Professor Richard Little, and today we're going to look at the deep history of Gill, Massachusetts. Gill is located right along the Connecticut River, and it is one of the best places in the world to study geology. Let's take a closer look. Is Gill one of the best places in the world to study geology? Well, there used to be a waterfall here, and we had dinosaur footprints too. In this program, you'll learn about how continental collisions created Pangaea, and learn how that supercontinent broke apart, creating the Valley of the Dinosaurs. There were rare armored mud balls, plus lava flows in that old valley. Later, glaciers came and went, and some strange, deep riverbed holes were formed. Let's talk about the creation of Pangaea, the supercontinent. If we go back to the Cambrian period, about 500 million years ago, we find that New England was not even part of North America as yet. There were small pieces of continents and islands that were offshore, maybe 500 miles from North America, and they collided with North America over time to assemble the supercontinent. This plate tectonic process involves subduction, where the ocean crust slides underneath the advancing tectonic continental plates. And now, here's the world's only subduction joke. There's a duck on a pond. It dives. That's subduction. Now this is important. Take a look at how Massachusetts grew as tectonic plates collided to make Pangaea. The shoreline of North America starts at the New York border. And then, thanks to plate tectonics and subduction, there is a collision that makes the first Appalachian mountain chain called the Taconic Mountains. We have several other collisions to finish the building of Massachusetts, and finally, by the end of the Paleozoic era, we have the big collision that brings Africa and South America, that were still together at that time, brings them into North America to build the great supercontinent of Pangaea. This geological map of Vermont illustrates our collisional history. Look at the layers. They go north-south. They represent great compressional events that came from the east. Note that if there's squeezing from the east, the folds that result go north to south. It's just like this car crash. The fender folds are perpendicular to the impact. And that's why all through New England, we have rock layers that are oriented in a north-south direction thanks to the great collisions that made Pangaea. Continental collisions are really complicated. Imagine what happens when 20-mile thick blocks of continents collide on the surface of the Earth. Amazing amounts of compression, faulting, folding, and metamorphism. One nearby place to go to see the evidence of these great Earth events is along Route 2 in Irving. It's informally called the Great Wall of Irving. The metamorphic rocks seen here were once mud and sand in several oceans that were here before Pangaea. The mud becomes schist after metamorphism, and the sand becomes quartzite. One of the final geologic events to happen here was the intrusion of magma, which is now granite. Granite can be dated radioactively, and intrusions like these are about 300 million years old, long before the dinosaurs. This is an amazing roadside outcrop. You know, if we could go to Mount Everest and bore 10 miles down, these are the types of rocks we would see. But here they are, exposed in the Great Wall of Irving. And now, death to supercontinents. All supercontinents have to die. Heat builds up underneath the extensive continental mass. This results in uplift. And then there's cracking. And it's this process that results in rift valleys. So as continents split, many rift valleys are created. The biggest ones develop into ocean basins, but many others remain as landlocked valleys, but are very important to geologic history. The Connecticut Valley Rift Fault runs from Keene to New Haven. In Gill, the eastern border fault runs north to south under the French King Bridge. Rift valleys are the key to understanding the geology of our region. In a rift valley, one side of the fault moves upward. That's where the mountains are. The other side is downward. That's where the valley extends. In the Connecticut Valley Rift, the east side is the upside, and rivers rush from those mountains on the east, bringing sediments into the valley to the west. The sediments pile up at the base of the mountains, forming alluvial fans. And then these merge into lakes and perhaps larger rivers in the lower parts of the valley. Gill is located in the valley part of the rift, on alluvial fans, shorelines, and lake beds. Did you know that the Rift Valley sediments, now conglomerate, sandstone, and shale rock, are 2 miles thick? And further south in Connecticut, the sediment thickness is 6 miles. This Rift Valley is from Death Valley National Park. There's mountains, a fault, an alluvial fan, and shorelines and dried up lake beds in the lowlands. Each has its own sedimentary rock type. The alluvial fan is made up of gravel, now a rock called conglomerate. The shorelines are made up of sandstone, and the lake beds are much more muddy. They would be shale. One of my favorite places to go is Death Valley, but not in the summertime. Death Valley, traveling through Death Valley is just like going through the Jurassic of western Massachusetts. Death Valley is part of an amazing Rift Valley landscape called the Basin and Range. There's uplift and stretching stresses that have extensively cracked the crust, and this is similar to what happened when Pangea split. Exploring Death Valley is like an adventure in the Jurassic time of the Connecticut Valley in Massachusetts, but there are no dinosaurs to eat you. In the Connecticut Valley, the major fault has uplifted mountains to the east and downdropped the valley to the west. There are alluvial fans against the mountain and lake beds in the lowlands. The rocks underneath Gill are composed of gravels of the old alluvial fans, now conglomerate rock. Sands from the old shorelines, which are now sandstones, and sandy muds from the old lake beds, and those are now shale. Dinosaurs walked along the lake shores looking for food and leaving footprints in the squishy, soft sediment. In fact, the Jurassic rocks of Gill have a lot of dinosaur footprints. Why, this may have even been a great spot for dinosaur dances every Saturday. There is a famous dinosaur footprint quarry along the river in Bartons Cove. It's the source of thousands of excellent footprints, some of which are at Amherst College's Benesky Museum. Here is a fun test of your ability to read the stories in the stone. A Jurassic dinosaur walked in the mud and through a puddle here at what is now Bartons Cove along the Connecticut River. But which side of this stone was the puddle? Well, it's the right side. The dinosaur footprint on the right side shows no speckling. There was a surface of water that intercepted the raindrops, but the left side of the stone is all speckled by the short shower that was passing about 180 million years ago. And now the world's most unusual fossil fish. Many fish fossils are found in old lakebed black shale layers. And one of these is truly unique. It's a fossil fish split by a fault. It's the original fish fillet. In this rare find, the fault moved through the fish laterally, but with no vertical offset, so both parts could remain on the same bedding plane layer. This fish was discovered and prepared by Dr. Harry Sharbow. And now, the amazing story of armored mudballs. Armored mudballs are very rare geologic sedimentary structures. Decades ago, I was the one that discovered these rare features in quarried blocks composing the cable anchors of the old suspension bridge that crossed the Connecticut River between Unity Park and Gill. The Unity Park cable anchors have been dismantled, and this large block with several beautiful armored mudballs is now preserved in the Greenfield Community College Geology path. So how do armored mudballs form? First, hard, dry mud chunks fall into a stream. They tumble down the stream and get round and soft and sticky on the outside rim. Pebbles from the stream bed then stick into the outside of the mudball, and that's what we call the armor. And finally, millions of years later, Hopefully they're part of a rock quarry so pieces can come out of the earth to be displayed. In 2023, a bill will be presented to the state legislature to start the process of armored mud balls becoming an official state sedimentary structure. These rare, funny, and photogenic geologic oddities deserve celebration and recognition. They should become an official state sedimentary structure, and Gill is one of the rare places in the whole world to see them. And now, let's go back to Mesozoic world events. Pangaea is splitting. Hot fluid lava flows across the landscape. Our Jurassic views would be much like Iceland. The lava becomes tilted by movements of the eastern border fault as Pangaea continues to split. Today we just see the edge of this lava flow. Lava is the rock called basalt, and it's harder than the surrounding sedimentary rocks. It becomes a ridge on the landscape. The lava is best seen in Greenfield. But it does form the dark rock seen from Route 2 and along Main Road. An important geological fact: basalt lava flowed here in the early Jurassic 201 million years ago. The weather was hot. We were close to the equator at about 15 degrees north latitude, and that's like Mexico today. The last ice age started about 2.5 million years ago, but the last maximum advance of the ice was only 20,000. That's like yesterday in geologic time. Imagine Gill under a mile of ice. As the ice moved, drumlins of glacial till were deposited, and mountaintops were eroded into a special form known as the roches moutonnées. Roches moutonnées are abraded and smoothed on the upglacier side as the glacier moves by, and they're plucked away on the southerly sides, creating a steeper edge. Drumlins, on the other hand, are made up of deposits of glacial till, and they tend to be steeper on the upglacier side, and as the glacier moves, they're smoothed out on the downglacier side. Gill has excellent examples. Here's a close-up of drumlins along Turner's Falls Road. Note that there is a steep side where the contour lines are closer together, and a gentle side where the contour lines are further apart. This is a topographic map. There's more information at the end of this program. Across the river in Northfield, there's excellent examples of roches moutonnées. The topographic map of this roche moutonnées shows the smooth side and the plucked steep side where the contour lines are much closer together. As the glacier melted, a great glacial lake followed the front of the melting ice. It started about 18,000 years ago in central Connecticut. As the ice melted northward, the lake followed the melting ice front. It got longer and longer. The lake reached Franklin County about 16,000 years ago. Eventually, the lake reached 200 miles long. And by 14,000 years ago, it had drained. Glacial Lake Hitchcock was a very significant event for Gill. Gill was right at the shoreline, which is 300 feet above sea level in this area. In some places, the lake had deposits from the melting ice and from inflowing rivers that completely filled it in. You could have walked across the lake at the French King Bridge Narrows. The Millers River built a large delta as it deposited huge amounts of sand, gravel, and mud into the lake. Here's a map of Lake Hitchcock in Franklin County from about 15,500 years ago. Note that the glacier was just melting out of Franklin County. And here's the same area after the deposition of the large Montague Plain Delta. Note that this gravel and sand deposit extended all the way to the hills of Gill and even a bit into Greenfield. Understanding this delta, the Montague Plain, is essential to understanding the many mysteries of landscapes and also the historical development of the region. Next in this program, you will see how the Montague Plain Delta was essential in creating waterfalls, which led to hydropower and the development of towns like Turner's Falls. This historic view illustrates the importance of waterfalls to human history. Water rushed through the factory, turning water wheels, and then exited through the tail race tunnels seen here. Today, the factory is gone, but the tail race tunnels are still visible. Here's an important note. All Connecticut Valley waterfalls are due to erosion of Lake Hitchcock delta deposits. In this Turner's Falls view, the flat delta top is here. Delta sand and gravel covered the area. Then the lake drained and the Connecticut River found itself on top of this bedrock layer and a waterfall developed. We will see a similar old waterfall story at Bartons Cove. Isn't it amazing how geology affects human history? And now let's take a look at a great glacier-esker delta story just up the road from Gill in West Northfield. Glaciers are made of ice and they obviously melt. There are loads of meltwater streams that gush out of ice tunnels. An esker is a curving ridge. This ridge is built of glacial stream gravels that were deposited in the tunnel. When the ice melts, the tunnel is left as a curving ridge. In West Northfield, a meltwater stream flowed out of the glacier into Lake Hitchcock. And in the process, it built a large delta. This delta today is mostly removed in the gravel operation, but you can still see the evidence of the esker and the remains of the glacier that are now the kettle ponds on either side. What a great Ice Age story preserved on the landscape. And now we have one more Delta story, the Sunderland Delta. Sunderland has a glacier meltwater delta situation into Lake Hitchcock, very similar to West Northfield. A meltwater stream rushed into Lake Hitchcock and built this beautiful delta. Deltas form as streams flow into lakes, ponds, or the ocean. They bring sediment into that standing water. Stream flow deposits, usually gravel, these are called the topset beds. At the shoreline area, sandier sediment is deposited, which then slumps underwater to form sloping layers, the foreset beds. And then finally, tiny particles of mud are washed into the deeper water of the lake bottom. In this beach puddle, you can see the delta structure deposited in the very clear water. Sunderland has a very similar glacial history to West Northfield. A meltwater stream rushed into Lake Hitchcock and built this beautiful delta. Revealed in the gravel pit are the two major parts of a delta. Topset beds and foreset beds. The topset beds formed by the inflowing stream, and note that they are coarse gravel from deposition of the fast-moving stream. This is a very rare view of the delta because after just a few days, the surface collapses and the slope looks like this. Lake Hitchcock drained by 14,000 years ago. Was there a great flood? No. Lake Hitchcock drained about 14,000 years ago. There was no great flood. The lake drained out in stages. After 14,000 years, the Connecticut River can come back to its valley. It meandered back and forth, creating terraces and floodplains. Sometimes the river found itself on top of bedrock, and that created some really mysterious landforms, ancient waterfalls and plunge pools. At the bottom of the Connecticut River are 5 holes that are over 100 feet deep. How did they get there? This is a great mystery, and about to be revealed is the whole story. Lake Hitchcock's deposits, especially the Montague Plain Delta, covered the present location of the Connecticut River with over 200 feet of sand and gravel, extending from the village of Montague to the hills of Gill. Once Lake Hitchcock drained, the Connecticut River was able to come back to its valley. It easily cut downward through the loose sand and gravel, but sometimes it found itself on top of a ridge, such as at Bartons Cove. The Bartons Cove Ridge is called the Lily Pond Barrier. As the river flow fell over the edge of this bedrock ridge, a waterfall was created. Falling water is very erosive, and it creates a plunge pool at the base of the waterfall. And these plunge pools can be quite deep. The Lily Pond Barrier illustrates 3 waterfall locations, each with a plunge pool. The third waterfall is at the Narrows and is the location where the eroding waterfall and plunge pool cut through the Lily Pond Barrier, and is the place where the Connecticut River flows today. With the erosion at the Narrows, the Connecticut River quickly cut its channel upstream until it encountered another bedrock barrier. And there another waterfall developed. After this location eroded, the river cut back until another bedrock layer obstructed the river flow, and there was another waterfall and plunge pool. There are 5 plunge pool locations. The 2 at the Lily Pond Barrier still have the preserved waterfall shape, and that's really important. The others have been eroded, and only the plunge pool preserves the story. The waterfalls in Gill have completely eroded through the waterfall producing bedrock. Let's go to Niagara Falls for a comparison. 2,000 years ago, Niagara Falls was a mile downstream. The waterfall is migrating upstream to where we see it today, leaving plunge pool deep holes in the riverbed. It was a smaller scale event, but can you imagine a mini Niagara migrating upstream underneath the French King Bridge? In conclusion, this is the best place in the world to study geology. There are amazing events recorded in our rocks and landscapes. And now you know. Let's take a look at topographic maps. Here are some quick and useful comments. We'll look at contour lines and how to link Google Earth views to free topographic maps. Contour lines are lines of equal elevation. Every 5th line is darker and is often labeled with the elevation above sea level. Many maps, as this one, are metric. 1 meter equals about 3 feet. Here is the drumlin along Turner's Falls Road that we saw earlier in the program. Contour lines that are closer together indicate a steeper slope. During the glacier movement, the steeper side of the drumlin is on the up glacier side, and then as the glacier moves along to the south, the drumlin is smoothed on the southerly side. But how high is this drumlin? This is one of the great things that topographic maps can tell you. By looking at the contour lines, we see here that there are 6 contour lines. So how high is this hill? That's right, it's about 100 feet high. Now, wasn't that fun? Finally, how would you like to link Google Earth views with topographic maps? Google Earth is just absolutely wonderful, but sometimes it really helps to have a topographic map to give you more landscape information. Here's how to do that for free. First, go to this website, and then you just click on this box, and it will load this application into Google Earth. Enjoy.